Welcome to everyone. In this module, we will investigate the materials used in running footwear, analyzing their mechanical and thermal properties, and evaluating their contribution to biomechanical efficiency and running economy. Running economy is a critical metric for endurance sports. It is indeed defined as the inverse of the energy required. A run is considered economical if it is efficient, and the efficiency is defined as the ratio between the mechanical work done and the energy required. First, the running economy is not only due to external factors. There is a strong innate component. Some individuals are naturally more economical, even at lower velocities, showcasing an optimized ratio between oxygen consumption and energy expenditure. Furthermore, more elastic muscle structure can inherently contribute to more economical running. However, while highly trained endurance athletes usually show greater running economy than their counterparts, it is influenced by many physiological factors, such as age, sex, body weight, muscle fiber distribution, and maximum oxygen uptake. There are also some biomechanical factors. An economical runner usually has a lower vertical oscillation, longer strides, and more constant velocity in ground contact. This gives the research a considerable margin for improvement due to the role of footwear and their materials chosen in their construction. Running shoes can directly impact cushioning, absorbing impact forces, and they can affect the stiffness of the stride during the push-off phase, affecting the impact forces transmitted through the body. And they can decrease the ground contact time. When a runner's foot strikes the ground, impact forces can range between 1 and 2.5 times their body weight. Modern shoes play a crucial role in helping the muscle manage these forces. Let's begin with the midsole. The thick layer between the outsole and the upper is mainly made of foams. Recent advancements have led to lightweight and elastic material like Pebax, Phylon, better in damping elasticity and durability, and EVA, ethylene vinyl acetate copolymer. These foams behave like springs. They absorb energy upon ground impact and return a significant portion of that energy to propel the runner forward. This energy return can potentially improve running economy by up to 4%, especially over long distances. Alongside, EVA, polyurethane, PU, is also widely used due to its durability, often maintaining its properties over distances exceeding 500 kilometers. However, the role of the midsole isn't limited to energy return. In recent years, there's been growing attention to the biomechanical effect of midsole hardness. While it's commonly assumed that softer midsole provide better cushioning and injury prevention, findings in the literature are inconclusive. Some studies have shown that increased midsole hardness may reduce peak vertical ground reaction forces and the stiffness of knee and ankle joints, suggesting that harder soles might help in dispersing impact forces more effectively and, paradoxically, reduce injury risk. Interestingly, shoes with softer midsole have sometimes been associated with a higher incidence of injuries, possibly due to the less stable supports during the stance phase. Moreover, it is not just about how soft or hard the whole midsole is, but where that hardness is applied. Research indicates that the rear foot region plays a key role in distributing vertical forces and influencing lower limb kinematics. A combination of a soft forefoot and a stiff rear foot midsole has shown promise in improving both cushioning and propulsion efficiency. In terms of structural innovation, Many cutting-edge running shoes now incorporate a carbon fiber plate embedded within the midsole. This plate acts as a rigid lever, enhancing foot stability and promoting a more efficient push-off. It can also reduce the muscular workload, particularly around the calf and ankle, areas prone to overuse injuries in runners. The bending stiffness is something considered for the improvements of the running economy. Nike refers to the teeter-totter effect as the lever-like mechanism created by the curved carbon fiber plate embedded in the midsole. When the heel strikes the ground, the plate flexes slightly and, together with a responsive foam, helps to propel the runner forward during the toe-off. This motion mimics a seesaw, here the name, and contributes to a smoother transition and improved running efficiency. Beyond traditional foams design, more novel approaches are emerging, such as the leaf spring-structured midsole, which replaces the uniform foam core with a segmented spring-like construction. Comparative studies between leaf spring midsole and standard foam midsole shows that leaf model can significantly increase step length and decrease both energy absorption at the hip and energy production demands at the ankle, potentially offering both biomechanical and metabolic advantages. Finally, it's worth highlighting once more the importance of lightness. As mentioned, the low weight of modern foam materials is critical, since heavier shoes demand more energy. To put this into perspective, for every additional 100 grams in shoe weight, oxygen consumption can increase by about 1%. Even the material chosen for the shoe upper, the part that surrounds the foot, influences the performances. The usual definition of upper is everything about the sole. In reality, it is the part that keeps the shoe in contact with the foot. For instance, a knit upper can enhance the connection between the foot and the sole, offering improved control over foot movement. Conversely, a mesh upper might be prioritized for its superior lightweight properties and breathability. Since the upper has a large area of contact with the foot, it has a great influence on the fit and comfort, which in turn has a notable impact on the kinematic and kinetic strategy of user during running. Common upper structures are typically either a mesh or a knit. A knit upper, for instance, is often engineered to create a more sock-like fit, which can potentially enhance the connection between the foot and the sole. This concludes our module on running footwear materials. In the next module, we will explore the materials used in mountaineering footwear, with a focus on insulation, protection, and structural performance under harsh conditions.